Hi, in this third video on hypothesis testing, we're going to look at another example of hypothesis testing, and we're going to break it down and show you how the p-values are actually being calculated by Stata in the background. So this example also comes from our textbook, and we're going to be thinking about whether or not subjects prefer images that are subliminally suggested in a psychological study. So, some of you may have heard of subliminal messages before, and some of you may not have. The idea is that they're trying to think about, psychologists are trying to ask, do people respond to things that they may not consciously be aware of? And one of the ways that they can test that is by doing something like flashing a word on a screen. Or flashing an image on a screen for a really, really short amount of time to where people don't actually aren't able to consciously process the fact that that image has been shown or that that word has been shown. They might not be able to tell you what that word is, but perhaps it still has some subconscious effect on them. And so this is a study that was conducted to try to figure out, does it have any effect when you put a subliminal suggestion for a certain message? So what they did in this study is they had participants choose between two images. There were two images shown to them 100 different times. They had two images shown to them. And they are supposed to pick one of those two images. And one of the images is subliminally suggested as the right image, and the other one is not. And so the question is, does the person tend to pick more of the images that received that subliminal suggestion? Now, remember, they're picking out of two images 100 times. So we're going to think about how many times out of those 100 did they pick the subliminal message? And if subliminal suggestions make no difference, then we would expect that exactly half of the suggested images should be chosen just out of dumb luck on average. Maybe not for every single participant, because just like if you flip a coin 100 times, it's not going to come up 50 times heads for every time. But if lots and lots of people conduct 100 coin flips, we would expect that on average they'll get 50 heads. In the same way, we think that in the population, if we were to continue conducting this experiment over and over and over again, that if the subliminal messages have no effect on what the person chooses, then the population average should be 50 out of 100 of the subliminally suggested messages that get chosen. Again, the idea is that if the subliminal message has no effect, then it should just be like a coin flip. Maybe the person happens to pick the image that was suggested, and maybe they don't. Whether or not the suggestion was there has no effect. So half the time they end up picking it, and half the time they don't, out of dumb luck. So we're going to use 50 out of 100 as our baseline. Now, do you remember what we use some sort of baseline to construct? We use it to construct our null hypothesis. And that's going to be what we do in step 1 of our hypothesis test, in addition to creating an alternative hypothesis. And so coming up with this baseline is going to help us to complete step 1. So step 1, that's how we're going to write it. Our null hypothesis, or H sub 0, or H naught, is going to be that mu, or the average in the population, is equal to 50. Of course, if that's our null hypothesis, then our alternative hypothesis is going to be something like mu is not equal to 50. But we didn't actually write a null hypothesis in this particular slide. We also could say that mu is greater than 50 if we wanted to say that the subliminal suggestion should have a positive effect on make people more likely to select that particular image. We could say mu is less than 50 if we thought that it was going to be that the respondents rejected it. They did the opposite of what was being subliminally suggested on average. But for now, we haven't actually written an alternative hypothesis because Stata is actually going to give 3 of them to us. We'll see that in a moment. All right, the other thing we need to do is select an alpha level, and we're just going to stick with the standard of 0.05. So here is some data that we can put into, or some code that we can put into Stata. I'm going to copy this, and I'm going to come over to Stata, and I'm actually going to create a do file to put this code in so that we can do it in a couple of steps. So the first thing I'm going to do is I'm going to paste this and just run these initial lines, which are going to put in the data that these researchers got. So rather than reading in a data file, we're just going to enter it in ourselves. And if we open up the data spreadsheet view, we can see that there are 9 observations, 9 people who participated in this, and these are the different scores that they got, arranged from least to greatest. So you can see that 4 subjects picked fewer than 50 out of 100 of the subliminally suggested messages, and 5 of the respondents picked more than 50 out of 100, more than half of the subliminally suggested messages. So that's the data that we've just entered into Stata. Now I'm going to go and I'm going to run this z-test command, which is going to allow me to run a hypothesis test with the null hypothesis that the truth is 50, right? That the mean in the population is 50. That's why I put this equal 50 here. So if we look at these results, like I said, it's giving us the results for 3 different alternative hypotheses that we could have chosen. I told you in the first video for this series that this is the main result that I want you to focus on if you don't have a reason to focus on another one. And that's because this is the non-directional or the two-sided hypothesis test. Or alternative hypothesis test. And so in this case, this is giving us a p-value if we're curious about how much evidence do we have to reject the null hypothesis and support the conclusion that the true population mean is something different than 50. Could be greater than 50, could be less than 50. This exclamation point equal means not equal in Stata. These are for if we have a directional hypothesis. So if our hypothesis is the mean is greater than 50, you can see we get a p-value of 0.27. Of course, the lower our p-value is, the more support we have for the alternative hypothesis, the closer we're getting to rejecting the null hypothesis. If, on the other hand, we have an alternative hypothesis that says, hey, maybe the mean is less than 50, then we get a p-value of 0.72. So you can see right here that we get the most support for this alternative hypothesis saying that the mean is greater than 50. In that case, we get a p-value of 0.27, which is the lowest p-value we get out of any of those 3. The reason we get the most support for that alternative hypothesis is that if we look at the mean value of our variable, the score that people got, the mean is exactly 51. Well, 51 is greater than 50, and so that's what we have the most support for, is that alternative hypothesis saying that the mean is actually greater than 50. All right, so let's focus though mainly on this middle hypothesis or alternative hypothesis, because that's usually what we use as a non-directional hypothesis. And as you can see, our p-value is equal to 0.54. So once we get a p-value, that means that we've completed step 3 of our hypothesis test. You can see that with rounding, we've listed the p-value there. So what is the 4th and final step of a hypothesis test? The 4th step is to compare the p-value to the alpha level, and our alpha level was the standard 0.05. Is the p-value greater than or less than 0.05? Of course, this is greater than 0.05. 0.55 is much larger than 0.05. And so we're going to say that p is greater than alpha, and therefore we fail to reject the null hypothesis, and thus our results are going to be inconclusive. Now, it's very important that when we fail to reject a null hypothesis, we don't interpret this to mean that the null hypothesis is true. It means that we couldn't find evidence to say that it's false. In other words, the results are inconclusive. That's one of the odd features of a null hypothesis or a hypothesis test, is that we often come to the conclusion that we can't conclude anything, that we don't have enough data to reject the whole null hypothesis, and therefore we're not going to conclude anything. And that's the case right here. So since this is our second example and we've learned now all of the building blocks of hypothesis tests, we want to dig a little bit deeper. And specifically, we want to dig deeper into step 3 of hypothesis testing, where we compute p-values. Now, what I'm about to show you isn't something that I expect you to ever do on your own, to compute your own p-values, because we'll just let Stata handle that for us. Um, but I want to give you one example in these slides, and there are also some other examples in the textbook. And we're going to build on the example that we just used, except rather than just trusting that Stata created the right answer for us, the right p-value for us, we're going to calculate it ourselves and show that we get the same result. So in order to calculate the p-value, the first step for calculating a p-value is to calculate a test statistic. In this case, what we're going to call a z-score, because there are different types of hypothesis tests, and the particular one that we're using right here is called a z-test, specifically with a one sample mean z-test. And so this is the formula for how we compute the z-score. It actually looks pretty similar to when we created z-scores before, when we were standardizing variables, talking about subtracting the mean from them and then dividing by the standard deviation. The difference here is that we're actually, instead of subtracting the mean, we're subtracting the value that we chose for our hypothesis, our null hypothesis. In other words, we're going to substitute in 50 here, what our null hypothesis said the population mean should be. And we're going to divide by the standard error, which is a measure, again, of how precise our estimate of the mean is in our sample, which is what's going to be right there. So that's how we're going to create the z-score. Of course, in order to calculate the standard error, we need to have another formula, and this is the formula that we saw before in lecture 6 for how to compute a standard error if we're assuming a normal distribution and that we actually know the true standard error of the population, or true standard deviation of the population. This is one of the downsides of this particular test that I'm showing you, is that it requires you to know ahead of time what the standard deviation of the population is. And in the real world, we usually don't know that. And so we're often going to use a t-test using the t-distribution instead of a z-test. And we talked about why we would use a t-test instead of a z-test, or a t-distribution instead of a normal distribution in lecture 6. So the same logic applies here, but for the sake of simplicity, we're going to demonstrate how to calculate the p-value from when we assume that there is a normal distribution and that we do know the standard deviation ahead of time. The textbook gives an example of how you can do a similar thing without that assumption by using the t-distribution, but for this example, we'll just stick to the normal distribution. Okay, so we have those two formulas. Of course, in order to calculate these formulas, we need to plug in a couple pieces of information. So in order to continue with this example, I'm going to go back to Stata. And what I want to do is I just want to get summary statistics for our variable score. So I'm going to type in some score so that I can get some basic descriptive statistics. And I'm going to move this a little bit farther up the screen. And you can see that we have 9 observations. Our sample size is 9, and our mean is 51. All right, so what I'm going to do is I'm going to come over to my Blackboard here, and you can see that I've already written down the formulas that I have for the calculating my z-statistic and my standard error. And of course, we saw in Stata that I have 9 observations and a mean of 51. And so I am going to write that down in my document, that we have a sample size, or an n of 9, and x bar, or the sample mean, is equal to 51. So that gives me most of what I need to be able to fill in my formulas and calculate my z-statistic. I still need one other piece of information, though, which is the standard deviation. Now, the standard deviation in my sample is shown right here, but to do a z-test, I actually have to assume up front what my standard deviation is. And you can see that when I ran the z-test, I actually assumed that the standard deviation of x is equal to 5. And so that's the value that I'm going to use to get the same z-score and the same p-value that we got in the in Stata. So now that I have all this information, the first thing that I'm going to do is I'm going to go ahead and calculate my standard error, which is going to be equal to the standard deviation of x divided by the square root of my sample size, n. Of course, the square root of 9 is going to be equal to 3. So my answer is 5 over 3, which I can simplify to be equal to 1.67. And if we go and look at our results in Stata, we can see that indeed it gave us the same result for the standard error, that it's equal to 1.66666 or 1.67. All right, let's go ahead now and compute the z-score itself. So the z-score is going to be equal to my sample mean, which is 51, minus my benchmark for the mean, which is 50, right? Because in our null hypothesis, we said that the true population mean we were assuming as a benchmark value is equal to 50. We're curious whether or not our sample departs from that. And I'm going to divide by the standard error, which is 1.67. So if I continue this, I see that I get 1 over 1.67, which is actually equal to 0.6 if you do that on your calculator. You might get a little bit of rounding error, so get a slightly different number. If we come back to Stata and we scroll down a little bit, we see that indeed Stata gave us a z-score of exactly 0.60000. Now, in order to be able to go from our z-score to our p-value, we actually have to go and look at the normal distribution. And what Stata is doing in the background is it's thinking about the sampling procedure. It's using math that's based on that. If you'll remember, anytime we create an estimate, we'll have a sampling distribution. In other words, a bunch of possible estimates that we could have gotten depending on who was drawn into our sample. And we're going to think about that sampling distribution, all those possible values, and based on the assumptions of the z-test, we're going to say all the possible values that we could have gotten are going to follow a normal distribution. As a result, we're going to think about how unlikely would it be for us to get a z-score of 0.6 in the standard normal distribution. In other words, how far away from the null hypothesis are we relative to all the possible estimates that we could reasonably expect to get if the true population mean is 50? And so if we go back to the normal distribution or the standard normal distribution, you'll remember that we said 95% of the time we get a value between -2 and +2, something in this range. And so we want to get more precise, though. Of course, we got a value of 0.6, which is more like right here. How often is it to get something this far away from 0? We know that it's not going to be that rare to get something this far away from 0 because there's a lot of area in the normal distribution that's farther away from 0 than 0.06. But we want to know exactly how far so we can get an exact p-value. Well, it used to be that people would flip to the back of their stats book and look at different charts to try to figure out an approximation. But now we can use software that will convert any z-value to a p-value. I'm going to skip over these couple bullet points, but we can also use a calculator. And if you click on this link, it'll take you to a web page where you can plug in different values to see what the probability of getting something that extreme in the standard normal distribution is. But in our case, we can see that if we put in 0.6, we get a p-value of 0.5485, which we can round to 0.55. In other words, there's a 55% chance that we get something at a 0.6 or farther on either side of the distribution from a 0 in the normal distribution. And that's what we're doing when we create a z-score on the way to computing a p-value. So if we come back to Stata, you can see that that's exactly what Stata gave us, 0.55 if we round, or if we have more decimal places, we get the exact same answer that way too. Part of the reason it's worth walking through all of this is that when you run a regression, when you do almost any sort of analysis in Stata or other statistical software, it's going to usually give you a p-value, but it's also going to show you a t-score or a t-score along the way. It's also going to spit that out. And if you're wondering, what is that number? Why is it always giving me a z-score or a t-score? Well, Stata is computing that on the way to getting its p-value. It's doing that in the background. Again, I'm not going to ever ask you to compute your own p-value by hand, but I wanted to walk you through once how it's done. All right. So a couple concluding things about hypothesis tests. So first of all, there's lots of other hypothesis tests that can easily be conducted once you understand this process of hypothesis testing. The 4 steps that we laid out in the first video on hypothesis testing, as long as you know those steps and understand them, you can work with a whole bunch of different types of hypothesis tests, including hypothesis tests for regressions or for correlations, for lots of different things. The key thing to being able to interpret a hypothesis test correctly is to always know what the null hypothesis is. And then you're accumulating evidence, you're looking at the evidence to say, can I conclude that the null is wrong or not? So as long as you know what the null is, you know what you're testing. So here's an example of a bit more complex hypothesis test. We'll come back to this example in future weeks. But the null hypothesis, we want to think about a population that's divided up into 4 different groups. Maybe we're looking at different states within the US and we've divided them into 4 regions. If we've done that, then a reasonable null hypothesis that we might have is that the mean is equivalent across all 4 regions, which is what we've written out here. The mean in region 1 is equal to the mean in region 2, which is equal to the mean in region 3, which is equal to the mean in region 4. And again, the mean could be for any variable that we're looking at. So for example, maybe we would say we're looking at welfare spending in different states, right? This null hypothesis would say that the average level of welfare spending is the same in the Northeast as it is in the Midwest, which is the same as the average in the South, which is the same as the average in the West. Again, that might not actually be true, but that's what our null hypothesis would be stating. It would have that as a benchmark, that they're all spending the same amount. If we have that sort of null hypothesis, then when we get our p-value, it's going to be telling us, can we support that? Or not, can we support that? Can we reject that null hypothesis? Or do we not have enough evidence? Are we going to get an inconclusive result? Or can we conclude that there are differences among the 4 regions, that at least 2 of them are different? Again, we'll look at that sort of hypothesis in more detail later. We might want to know whether or not the number of visits to an emergency room varies by day of the week. Again, we could come up with a null hypothesis saying that the mean number of visits is the same for all 7 days of the week. In other words, the mean number of visits on Mondays is the same as the mean number of visits on Tuesdays, which is the same as the mean number of visits on Wednesdays, etc. So the main point here is just that there's lots of ways we can write hypotheses and we can test lots of different things with hypothesis testing. All right. I have a few review questions for you as the very last slide in this lecture, and this is really to just help you think about what to focus on as you go over the material from this chapter. That's it for hypothesis testing.